Thank you very much. I'm very honored to be here. I appreciate the gracious hospitality we've been given, and looking forward to giving you a presentation on a project. I am the project manager for this particular project, and I've cobbled some things together to talk about New Bullards Bar Dam. First, how am I going to present this? I'm going to present kind of two pieces of the puzzle here. The first piece, I'm going to talk a little bit about background, and I'll talk a bit about forecasted informed reservoir operations. And then I'm going to talk about the project itself. And the project itself is really all about, and you're going to hear me call it FIRO, and that's just F-I-R-O, because that name, Forecast Informed Reservoir Operations, is very long. So where are we located? We're located here in the United States, on the western part of the United States, located there in the red in California. And more specifically, we're in Northern California. So I think it's important first to kind of understand the complexity of how water management's done in the United States. And my colleague touched on this a little bit, and I'll touch on it a little bit more. But we have the federal government, we have the state government, and then we have local agencies. And when we talk about these large multi-purpose projects and multi-purpose dams, it's typically all three are participating in the construction of a dam. Now, in some cases, maybe the Corps of Engineers is the owner, operator, and actually constructed the dam. In the case of New Bullards Bar Dam, you had the Corps of Engineers participated, and that means the federal government sponsored a project that was going to be a multi-purpose project, and that's New Bullards Bar Dam. They participated by sponsoring the flood management piece of it, and then it's the local agencies that pay for the water supply, in this case, the recreation and some of the other benefits. Now, when the Corps of Engineers sponsors a project, they want that dam to be operated in a certain way. And so in the United States, that's called a rule curve, and I think I've seen some presentations here in Japan that are very similar to that. And that rule curve means there needs to be a space in the reservoir, and that's gonna vary throughout the year. So in January, the space has to be very big. In February, March, April, it starts getting smaller and smaller, but you've always got to keep that space available for flood control. And so it's up to the responsibility of the agency to honor that contract and keep that flood space. So that's how the Corps of Engineers and the local agencies work. And then there's the state agencies. The state agency, in some cases, the Department of Water Resources, they do have a water supply. They've built the State Water Project. That has nothing to do with this project, but they also organize flood management. And so they're a partner in terms of flood management by providing research and benefits and sponsoring certain kind of projects. And you'll see that in just a little bit. So the state's involved as well. And then there's the local agency. And so the local agency that I'm going to talk about, and I'd like to give them some credit, is the Yuba Water Agency. And so Yuba Water Agency is an agency that owns and operates this dam. And so it was funded by a combination of funds back in 1970. And now they operate this project in order to meet all the objectives of the original intent of the project. Now, in addition to these federal and state agencies, there's regulators. And regulators are there to regulate several things, including the safety of the dam. And there's two regulators in California. One is the Federal Energy Regulatory Commission. You heard about them, FERC. And then on top of that, there's an independent, and this is an organization I actually was in for 30 some odd years, is California's Dam Safety Program. And so they're also regulating the safety of the dam. So it's very important to kind of understand how all these different agencies work together on these very complex multi-purpose projects. So it's also kind of important to understand the geography of what we're doing here in California, and in particular, the Central Valley of California. So when you look at California, and our project's up there in the north, and so the red circle represents the Sacramento River flood control system. I want to explain that. And then the blue is where New Bullards Bar Dam is and the project that we're working on. So the Sacramento River Flood Control System, it was actually created in the beginning and right after the gold rush. So right after 1850, you've had a lot of population coming in. And when you look at the geography of California, you have very high mountains to the east, up to 14,000 feet. Then you have coastal mountains to the east, and those are much lower. And then you have this Central Valley, and the Central Valley is basically a big plain that was established over millions of years and is basically a floodplain. And so as you can imagine, after 1850, when the populations start coming in, they had to protect those populations. The cities start growing. They had to protect the population, and they did that by the construction of levees. They also had to protect their farms, and so there was construction of levees. And so between 1850 and about 1870, these levees were just being constructed haphazardly, meaning there was no coordination. They were just being constructed. They were failing fairly regularly. And so the Corps of Engineers came in, and in about 1870, they started establishing what's now called the Sacramento River Flood Control System. And it's an important understanding that the entire Central Valley, both in the north and in the south, are protected by these levees. And these levees, remember, are built anywhere between 1850 and generally 1900. And then in about 1940, 1950, then large reservoirs started to be constructed. And so in Northern California, we have very big reservoirs. We have some of the ones that are working in conjunction with flood control include Shasta Dam to the very north, Oroville Dam. You heard about Oroville Dam. Oroville Dam's a large dam just north of New Bullards Bar. And then you have New Bullards Bar Dam. And then you have Folsom over the top of Sacramento. And so collectively, this system works together. The system of the dams and the flood control facilities and those operational rule curves that are on each one of these major dams, and they're all trying to prevent these overtopping or failure of the levees. And again, these levees are very old. So it's important to kind of understand how this kind of system was put together because that's what we've been trying to fix over the last several decades. So what's been happening? Well, right after 1850, you start having a lot of floods throughout the entire Central Valley. Levees were failing normally. And then in 1955, after the populations were very established, you had some significant flooding in Yuba County. And Yuba County is the area that we're trying to protect with New Bullards Bar Dam eventually. But in 1955, a major flood caused the creation of the Yuba County Water Agency. And so their purpose, now it's a new local agency, and the purpose of this local agency is not only water supply, but is really instituted for the purpose of flood control. That was really the reason. But then after New Bullards Bar was constructed in about the late 1960s and 1970s, and it protected the city more. However, there's still flooding. There's still these levees that are old and 150 years old. They're still failing. Anytime you have these large storms that come in, you get the levees failing, and as a result of that, you still have this significant failures happening not only in Yuba County, but throughout Northern California. And so these flooding instances cause obviously millions and billions of dollars of damage, as well as loss of life. So after one of the major floods in 1986, and then another flood in 1997, where cities were inundated by floodwaters, the Yuba County Water Agency decided to step up. And they decided to step up to try to develop a plan, and a plan that's somewhat ambitious. And it's ambitious in terms of what's our norm in California. And what I mean by that is they wanted to try to get to a 500-year level of protection. Now, when we compare 500-year level of protection, compare that to the risk of dams and the risks that we generally look at, we're usually in the 1,000, 10,000, 100,000 kind of levels. That's just not practical when we talk about levees. So the idea was, let's try to get to a 500-year level of protection. And how are we going to do that? We have to address the levees, and then we have to look at the dams. And so the first thing that happened in about 2001 is the state of California came forward and provided about $100 million to begin the development of levee repairs in and around Yuba County. So that was a good boost to get the thing started. And remember, most of the levees in California, when they fail, they're actually failing as a result of underseepage, not so much overtopping. These levees are old. They're built on sands, natural sands deposits, etc., and that's typically how they're failing. Now, in about 2003, if I remember correctly, there was a major hurricane in New Orleans. And in New Orleans, you had this hurricane that actually failed many of the levees in New Orleans. And that's actually what kick-started a program called Flood Safe California. It was actually a program that I ran for a couple years. And the idea that we had was we got a bond measure for about $5 billion. And this $5 billion was going to be used statewide to improve flood management statewide. But the bulk of the money was going to be put into Northern California. And the reason it was going to be put into Northern California is the state of California just lost a $1 billion suit because of those failed levees. And so there's a combination of issues that had to be taken care of. First of all, it was the local agencies that were allowing the risk to go higher by allowing folks to just go ahead and construct housing behind these poor levees. But it was the state of California that was taking on that risk. So this very complex legislation moved forward to start putting the onus on the local agencies. If you don't have 200-year level of protection, you can't increase your population anymore. And so that was the incentive for the locals to start putting into the money with the state, and the state provided several $1 billion to start improving the levees. So this was a huge influx of money, and it provided a significant amount of flood protection by improving those levees. You could see on the picture over on the left, there's huge populations behind some of these levees, and so it's quite significant. Now, I think it's important to also understand, because we're going to now start shifting into FIRO, or flood-informed reservoir operations. And when I talk about that, the only way it's going to work is if you could actually forecast weather. And there is certainly uncertainty and a significant amount of uncertainty in forecasting weather. However, we're a bit fortunate on the western part of the United States, unlike some of the Midwest states, in that we can actually see the storms developing, and we could actually tell where the storms are developing from, which is an absolute critical point. And so if a storm's developing up in the Alaskan area, then that storm's going to be very cold. That storm's going to come in and it's going to hit California, and it could have significant precipitation, but that precipitation is going to fall in the form of snow. And typically on a very cold storm, that could be a snow level of 2,000 or 3,000 feet, and then all the way up to 12,000, 14,000 feet, it's all coming down as snow. And so that provides local flooding, but it doesn't generally provide the regional flooding that you see. Now, the difference between that and another type of storm is what we call, the media has called it the Pineapple Express storm. We call it atmospheric rivers. These storms are created in the Hawaiian Islands. In the warmer waters near the Hawaiian Islands, they come straight through and they funnel right into California. Now, they're producing a significant amount of precipitation just like the northern Alaskan storms do. However, the biggest difference is now they're coming in as precipitation. And so we have some of these atmospheric rivers creating precipitation as high as 12,000 feet. And in some cases, you have snow in the mountains where these warm storms are coming in. They're melting the snow, and that's what's been creating these huge flood scenarios in California and other parts of the western United States. Another issue, of course, is climate change. Now, climate change in California is very uncertain. I was running a program for the groundwater program at one time, and we had to consider climate change. And so we studied that, and we looked at the various studies, and they're all over the place in terms of precipitation. Some studies are predicting less precipitation. Some studies are predicting more precipitation. We're all over the place in that prediction. But there is consistency among the studies that no matter the precipitation, whether it's minus or plus, it's going to be warmer. And I think that's what we've been experiencing over the last 50 years, is again, The storms are going to come in warmer. They're going to cause more precipitation and less snow, which creates all kind of problems for us. It creates the problem of water supply because historically, the snowpack was really a major reservoir for the state of California. Now that's going to get higher and higher and lower snowpack, which is going to create some significant problems. In addition, that precipitation is going to cause more flooding. The problem with climate change is it's very uncertain right now. We don't really have a good grasp on how climate change is going to affect us, but we think it's going to affect us negatively. And so we need to start preparing for climate change. And so that brings us to forecast-informed reservoir operations, and we just call it FIRO. And so there was a great question earlier in the in the previous presentation, and the question is, well, why don't you just build more dams? Well, in California, that doesn't seem to ever happen. We just can't seem to get the population to agree to construct any new dams. The only dams that are being constructed, and there are some major dams, $5 billion projects currently on the books right now that may get built in the next 10 years. These are all off-stream reservoirs, and so they're only for water supply. So the way these are going to be working is as the water's coming down the river during a flood situation, they're going to pump water into these major reservoirs for the purpose solely of water supply. But it's not going to really help us from a flood control standpoint. The last major, and I'm talking about the big dams, the last major flood control dam is called Auburn Dam above Sacramento. And at the time, Sacramento had less than a 1 in 100 year level of protection. Even that got shot down. So this is shot down generally for environmental reasons. And I just don't see us building any more dams on rivers in the state of California, which really prompts us to do things like forecast-informed reservoir operations. So why are we doing this? We need a smarter way to work with the existing infrastructure that we have. So we've fixed the levees to a point. They're still 150-year-old levees, but we need a better way to actually operate the reservoirs, and that's where FIRO comes in. And so that's what we're going to be talking about over the next several slides. Now, when we talk about FIRO, it could be used for a variety of reasons, and it could be used for a combination of reasons. So first of all, you could use FIRO for flood control, and that's what you're going to hear about today with New Bullards Bar Dam. You could use it for water supply, and how would you use that? You would start encroaching into that flood space if you're able to forecast and accurately forecast the weather. So you could escape it and then use that cushion that you have within the reservoir to knock off the peak of the storm. So that's how FIRO would use for water supply. It could also be used for environmental resiliency as well as even groundwater improvement. Or it could be used for a combination. And so when we talk about FIRO, we have several projects going right now in the state of California. And New Bullards Bar is about in the middle of its maturity. And what I mean by that is we've been studying it for quite a while. We've been analyzing the data, moving it forward. And in fact, at New Bullards Bar, they are using weather and forecasting to operate their dam right now, but they're not outside of that flood. They're never going to work outside of that agreed upon agreement between the Corps of Engineers and the local agencies. Now, there is another project in Mendocino near the Napa area that's going towards San Francisco, where they're very close to making an agreement on the rule curve. Now, this is actually a Corps of Engineer project, but collectively they're getting close, and they think by the end of the year they're going to have an official document that's going to allow them to encroach within the reservoir, within that rule curve and within that flood capacity. So when we talk about flood-informed reservoir operations, it's essential. I explained the complexity of the management system of water in California. You have federal, you have state, you have local agencies. They have to work together in order to move this forward. And they have been. Over the last decade, they've been working together in a variety of ways. They've been improving and participating collectively to install better instruments, both on the ground, rain gauges, river gauges, atmospheric gauges. They've even started looking at airborne instrumentation to understand the storms a bit better. They've also been developing their models and checking their models and going back with their models against various storms. And they've been continually improving on this system of forecasting. And so as this gets better and better, we think that we're going to be able to forecast longer and longer. And I think that's really the goal, and that's what we're trying to achieve. So now let's get into the project that I'm actually the project manager for, and this is the project that we're pretty much finished with design. So this is New Bullards Bar Dam. It's one of the largest concrete dams in North America. It's a little bit over 600 feet tall. It's a variable radius arch dam. It's an amazing structure, so it's curved both ways. Fairly thin for a concrete dam. And it has about 1 million acre-feet of reservoir behind it, just a little bit under that. And so some of the major features, of course, it's a multi-purpose dam, so it's also generating hydropower. So you have a penstock, and that penstock feeds a powerhouse that's thousands of feet downstream. And then the other major feature is a radial gate. And so right now, you have the radial gate on the left abutment of the dam, and that's actually what's controlling floods today. So when you start encroaching within that flood space, they have to open those radial gates in order to get us back down into the flood space. And they've also got requirements of keeping the flow to a particular amount right now. And they generally like to keep it below 50,000 CFS. And now this reservoir actually operates in conjunction with Oroville. And what I mean by that is this has an arm of the river, Oroville has an arm in the river, and then in Yuba County they come together. So this rule curve has to complement Oroville's rule curve, and it does. And so any modifications we do with this project, because of FIRO, we're going to have to do that with Oroville, because they're going to work together to protect the community downstream. So what this project's basically doing is now we're going to build a project that gives us more flexibility. And so when you look at the existing system right now, the spillway's at the top of the dam. And at the top of the dam, you don't have much head, so you can't get that water out quick enough. And you don't have a whole lot of volume. So this particular design is to put in a new spillway, lower it by about 30 feet, and that gives us both the power to drive water out quicker, as well as additional flood space of about 120,000 acre-feet of available storage. And now we're able to get about 35,000 CFS out at the bottom of the flood pool. So we're already at the bottom of the flood pool. If they see an oncoming storm, they're going to even reduce the reservoir even more, which provides more flood management for downstream. And so that's really the idea of this particular project. And so the project requirements that came to the design after going back and forth and checking the flows between the reservoir and the inflows and the outflows, and then how that would affect the levee system downstream. It was an iterative process, and we came up with the most optimal point would be about 35,000 CFS capacity at the bottom of that flood pool. This also is going to provide us a redundant spillway. Hopefully, this particular dam has never a case like what we've seen at Oroville, but if it does have a problem in the future, this is going to be a redundant spillway, so it's also going to help that way. The other critical component of a project requirement is we had to design the project so that it would not affect the operations of the current reservoir. And so we had to make sure that we're not emptying the reservoir, we're not lowering the reservoir in any sense of the way during the construction of the project. And then there's a major arterial road that goes over the top of the dam, and it really serves the community upstream and downstream of the dam, and it's really the only road that you can get through, and without that, folks would be pretty much trapped in the area or have to drive hundreds of miles around to get to where they wanted to get in the area downstream of the dam. So another requirement is to make sure that road is open during the entire construction of the project. So those are the project requirements that we're going to do. And so when we started the design, we started with the design is looking over here on the left abutment. We wanted this spillway to be completely separate and apart from the existing spillway. And what we were going to do is there's a rock knoll, and so we looked at designing a tunnel through that rock knoll. that created a couple of problems. The biggest problem was a cofferdam. If we put this tunnel through the rock knoll, we'd have to move the structure somewhat upstream, which would require us to build a cofferdam in the reservoir. That cofferdam in and of itself was going to be $50 to $100 million just to build the cofferdam. And there was going to be some significant risk associated with the development of that cofferdam. Additionally, there were some hydraulic problems associated with going through that tunnel. And after a value engineering study that was completed at about the 30% level, we decided we're going to abandon the tunnel, and all we're going to do is we're going to cut a notch through the left abutment and build a new structure, similar but more up-to-date than the existing spillway structure. So I'm going to kind of go through the various features of the project one by one, but basically the one piece that we're going to talk about is the upstream and how we're going to deal with the upstream area. We're going to talk about the control structure. We're going to talk a little bit about the spillway chute and then a discharge channel. So I'll go through these kind of one by one quickly. But obviously there's a significant amount of analysis that have to support this particular design. We started this design in about 2020 or so, and we've completed the design probably about a year ago, and we're just waiting for some final approvals. But obviously you have to understand the geology really well. The rock is actually very good, very strong, competent granitic rock. It's a bit porous on the downstream end, but it's very tight where the control structure is going to be. And so at the control structure, we don't anticipate too much grouting necessary. The actual structure itself is complex, and we did a three-dimensional finite element analysis. Typically in California, structures and dams are driven by the seismic load. And I think it's important to understand in this particular part of California, it's relatively low. And I say relatively because, like Japan, California has a lot of earthquakes. But the major earthquakes, the big earthquakes, are in the Bay Area and in Southern California near Los Angeles. And these are the earthquakes that can produce magnitude 8s and well over a G peak ground acceleration. And they're very frequent. They happen every 50 to 100 years, some of these major earthquakes in the western part of California. Now, when you get to the eastern part, it's significantly different. So the load itself is about 25% of what we see on the western part of California. And in addition to that, the frequency is much, much less. So the return periods of these major earthquakes are significantly less than the 100-year frequencies that we see on the West Coast. So that just basically made this analysis, or more importantly, the structure, a much simpler structure to design. It's a very complex but very robust structure that's going to be constructed in there. We, of course, checked the hydraulics with the physical model. This physical model was in the same laboratory that I think Dean talked about at Utah State. We also complemented that with a computational fluid dynamics model, and the CFD model and the physical model matched almost perfectly. This allowed us to fine-tune the design of the entrance and exit points at that control structure, and we were quite happy with that. So now let's get back into the features, the approach channel. So the approach channel is going to actually serve as the cofferdam. So by moving the structure downstream in the second phase scenario that we came up with in the value engineering, that's allowing us to use the natural topography to be the cofferdam. And the approach channel will be excavated, but it's going to be the last piece that's done. So we're going to construct all the downstream pieces first, and then when the reservoir is low, that's when we're going to do the excavation of the approach channel. So that protects all construction downstream, and it's the most efficient way in terms of cost to deal with the cofferdam. The control structure itself, it's going to have two sets of gates. In the old structure, we only have one set of gates, and those are the 3 radial gates. In this case, we're going to have 2 sets of gates, the first guard gates, and these are like roller gates, and then downstream are the radial gates, and the radial gates are actually going to be the ones that are controlling the flow. The other ones are just for guarding the radial gates. There are going to be submerged gates because now we're 30 feet lower. So you got bottom and top sills on both the radial and the guard gates. And then you have the spillway chute. The spillway chute's very traditional, meeting current standards of today. The one unique thing on this one is, unlike Oroville Dam, we're actually developing a flip bucket at the end, which is going to lead to this discharge channel. So half the spillway is a concrete structure. The downstream half is a discharge channel that's just going to be excavated. And when we design the spillway, we're actually shooting the water over the top of this entire discharge channel. So the water's actually going to hit, it's going to disperse, and then it's going to hit at the downstream toe of this discharge channel in a natural pool. So the discharge channel itself really is not going to see too much flow. But it is an extremely steep canyon here, and so that discharge channel is extremely steep. And then finally, the Marysville Road, it'll stay in operation during the entire construction. We're going to move that road in order to accommodate the new structure, but that move is going to happen over hours so that there's never a break in traffic in this particular project. So where does that leave us with the project? Where are we on the project? We have pretty much all of the approvals. What often takes time is the environmental documentation in a project this large. We've been working on that for years. The environmental documentation is now complete. We have our two regulators. They're wrapping up their final. They've been reviewing the 30, 60, 90% design. We think we've resolved all their comments, so we're expecting approval from those two regulating agencies in the next couple of months. And so there's really just one hang-up right now, and that's a FERC license. So when you construct a major dam like this and it has hydropower, FERC is not only overseeing the safety of the dam, they're also licensing the hydropower of that particular project. And so when you have a major modification such as this, you have to get a license amendment. And that generally takes a couple of years. We're about a year into it. And so that's really what's holding up the final construction start date. But we expect construction to start in about 2027. And then this is going to be about a 4-year construction window to do all this work. So the benefits are obvious. The benefits are really to reduce that flood risk downstream. And what is it going to reduce it by? So remember, you have all these levees downstream. They have been rehabilitated. There's been billions of dollars invested in the levees in the Central Valley. However, they're still 150 years old. And so what we're trying to do is we're trying to reduce the level in that levee. And that would, of course, not only increase the return period of any overtopping that occurred on those levees, it's actually going to lower the level, which has a significant and exponential relief of pressure at the toe of these levees, which is really what's been causing the failures of levees in Northern California over the last several decades. This also gives us that operational flexibility. We're going to be able to release flows much more sooner than what we have in the past. We're going to be able to release more flows and higher release capacities. This is going to provide that redundant spillway. Right now, this is a concrete arch dam, and it's got rock abutments, but it currently overtops in the design flood, the PMF. But it's only overtopping by a few inches, actually. And so with this new spillway, that's going to eliminate even that issue. So it provides some additional protection against the extreme flood conditions. And then we talked about climate change. This is just going to give us one more tool in the toolbox to deal with climate change. As we learn more about it, as we see warmer weather, this allows us to operate that reservoir a little bit more efficiently to deal with some of those uncertainties that we're going to have to deal with in the future. So the future operations, as I previously mentioned, it's really a combination of organizations that's been working on this particular project, and that's going to continue. They're already doing forecast-informed reservoir operations on many projects in California, and there's 2 that are very close to actually changing their rule curve. These are actually owned by the Corps of Engineers, but the local agencies have been working closely with them because they're in need of additional water supply. New Bullards Bar, remember, it's a little bit different. They're not trying to increase water supply. What they're trying to increase is more flood protection for this particular reservoir. There's really the other issue, there's always a natural conflict between water supply and flood management, right? You want more water to store because you need it in the summer, but you want more space because you need that space for flood control. So that's a natural conflict. But in this particular case, and in all the cases, we're talking about one, the same agency is making that decision. So the agency that's dealing with flood management is also dealing with water supply. And so it's going to be their decision to balance those two as they go through it, not only on this project, but on all the other projects. Now, more importantly, is it the community that's benefiting from a water supply standpoint is also benefiting from a flood management standpoint. So you don't necessarily have group X fighting with group Y, one wanting more water supply and one wanting more flood management. And so far that hasn't been a particular issue where you see that particular conflict. So with that, I'll end my presentation and look forward to questions in a bit. Thank you.
Mr. Gutierrez, thank you very much for your insightful presentation.
Thank you.